last part of the exam. So let's continue our discussion of Gauss's law. Right now, last day we looked at an example of a charged spherical insulator, and we found the electric field inside that charged sphere. We used Gauss's law to find it in a rather simple way. So Gauss's law is going to be useful, most useful for us, to find the electric field of charge distributions that have a high degree of symmetry. So some of those degrees of symmetry would be spherical. Spherical symmetry, and whenever I have a sphere, I could have a sphere that is a conductor, right? Or an insulator. An insulator, if it was an insulator, the charge could be distributed throughout its volume, right? It wouldn't all want to go to the surface if it was an insulator. But we could use Gauss's law even if the charge distribution wasn't constant, if it wasn't uniform. But the charge distribution would have to be radially symmetric, meaning only depend on how far you are from the center, and we could still use Gauss's law. Right? But you could imagine a insulating sphere where there's not a lot of charge at the center, but it kind of piles up linearly as you go outwards. Or you could imagine it the other way around. There's a lot of charge at the center, and it kind of bleeds out as you get to the edge. As long as it's radially, it only depends on the radial coordinate, r, you could still use Gauss's law, and it would still have spherical symmetry, even though the distribution of charge isn't constant, right? So that's spherical. Now, then we also have cylindrical symmetry and planar symmetry. So let's talk a little bit more about each of these in just a little bit more detail. And I'll write on the board here Gauss's law again. So Gauss's law just says the electric flux through any closed surface is just equal to the enclosed charge divided by the permittivity of free space, epsilon naught. Right? So this is Gauss's law, and how we practically utilize it is we calculate the left side. In situations where there's a lot of symmetry, we can easily calculate the left-hand side, and then we equate it to the right-hand side, and we solve for our electric field. That's the basic process here. You got to calculate the left-hand side, calculate the right-hand side, set them equal to each other, solve for the electric field. It's only really useful, though, when there's a high degree of symmetry. Okay, what is electric flux? Well, electric flux is the surface integral of E dot dA, and in general, your surface can be open or closed. Gauss's law is speaking only for closed surfaces. That is ones that have no holes in them, right? Now, what is Q enclosed? Well, Q enclosed could be a point charge. It could be a linear charge. It could be a surface, or it could be a volume charge. right? So if it was linear charge, we could say the total amount of enclosed charge inside my Gaussian surface. So the enclosed part here refers to whatever surface you construct. Right? You're calculating the flux through some surface, and you can choose whatever. It's an imaginary surface, but you can choose. It's a mathematical construct which you use to apply Gauss's law. So the enclosed charge here would be the integral of lambda, say dx, right? And lambda could in particular be a function of x. Right? So you just integrate it to get the total amount of charge. For a surface, your enclosed charge is really a double integral of eta dA. You have to integrate my surface charge density over the area of the surface. Right? It could be, again, it could be a closed surface or an open surface. And then volume charge is going to be a triple integral of rho dV. And dV is that little volume element. So rho is charge per unit volume multiplied by a little volume element and then integrating over that volume. So for instance, in Cartesian coordinates, dV is dx, dy, dz in Cartesian coordinates. But in spherical coordinates, your volume element is r squared sine theta, dr, d theta, d phi. Right? Okay, but again, we're just doing simple integrals here. They'll always, for the most part, reduce to a kind of a very simple form. But the most important point is being able to set up the problem correctly. So let's just look at a simple example here, continuing on with spherical symmetry, but let's look at nested conducting spheres. So let's say I have a big sphere and it has a thickness to it. Okay, and the inner radius is b, the outer radius is c. And then right at the center of this sphere is another sphere, and this sphere at the center is not hollow, it's a solid sphere. And this one has radius a. All right, now let's say that that sphere at the center has charge q on it. And let's say that the outer sphere has charge -2 times q on it. So remember, it's a conductor, so the charge can kind of freely move about. So let's ask a couple questions here. So first of all, let's ask a question about the charge. So how much charge is on surface, let's say R equals A. And give you a couple. So take out your voting cards. So is there greater than Q, less than Q, equal Q, or 0? So on the surface of that inner sphere, how much charge is on this surface right here. And we'll take a vote. 3, 2, 1. All right, now I want you to explain to your neighbor what the correct answer is and try to incorporate Gauss's law. So use Gauss's law to explain your answer. Okay, so most of you got it correct the first time, saying it was charge Q on the outer surface. But why, according to Gauss's law, must all that charge be on the surface? Anyone have a reason using Gauss's law? Yes.
If you were to look at a Gaussian surface that was super close to the surface but not touching the surface, you would find that the electric field within that surface is zero, or within that Gaussian surface is zero. So then all of the charge must be outside of that surface, but still within the sphere A. So all of the charge must reside on the surface of sphere A.
So what was the very first part of your argument again was, because I didn't hear quite the beginning. So if I make a Gaussian surface like this, it's a mathematical construct, right? Make a small Gaussian surface, and what did you say about that surface again?
It was very close to the edge, but not touching the
Okay.
edge.
So it's just inside, it's just a little bit less than R equals A.
Yeah, and if you were to look at the electric field within that Gaussian surface, you would find that it's zero. Or you'd find that there's no charge within the electric field. Yes.
Why? No. Elijah.
Because electric charge is stored on the earth. Because excess charge is always on the surface of the conductor.
Okay, but why according to Gauss's law? Yeah.
If you had any electric field through that smaller Gaussian surface, then the conductor would not be in static equilibrium. So basically, then you need, you need to have no electric field through that Gaussian surface. You need to have zero flux as well, right? And if you have zero flux, you have zero charge inside there, which means all the charge must be outside.
Okay, good. So putting all these ideas together, excellent. We would say we're assuming there's this thing called static equilibrium, right? Nothing's moving. If no free charge is moving inside the conductor, that means the electric field inside the conductor must be zero, right? Now, when we apply Gauss's law, and if the flux is zero, electric field is zero inside, that means there can't be any charge inside it as well. Excellent. All right, so zero is the right one here. Now, Q. But the electric field inside this conductor is zero. So I can write the E field here. E is equal to 0 anytime your radius is less than A. All right, so how much charge is on surface R equals B. And that entire outer shell has charge negative 2Q. So I'm going to change the options there a little bit. I'm going to say, I'm just going to make this I'm just going to replace the Q's with negative 2 Q's. So how much charge is on the surface R equals B? Is it greater than negative 2Q? Is it less than negative 2Q? Is it equal to negative 2Q? Or does it equal 0? Give you a moment to prepare your vote. Clarification question?
Yeah, greater in absolute value or just in, like, you know what I mean? Like, is
Consider the negative sign. So, for instance, negative 1Q or negative 0.5Q would be greater than negative 2Q. Okay, let's show our vote on 3, 2, 1. All right, 30 seconds. Explain to your neighbor, using Gauss's law, how much charge is at R equals B?
I was thinking it's somewhere
So like, it's one thing about this particular chapter, because
All right, get ready to prepare your vote. We'll take another survey here. The count of 3, 2, 1. All right, so A is correct. There's more than negative 2Q. How much more? Negative 1Q? All right, that's correct. Why is there negative Q on that inner surface, R equals B? Yes?
Using the same concept, you should have an electric flux through a Gaussian sphere that would be just below radius C. And so there could be no charge enclosed, no net charge enclosed inside of that Gaussian sphere. And you have positive Q on a small thing, and so you have to have negative Q on that surface B to cancel that out.
Okay, excellent. So if I create another Gaussian surface, and this one is just the cross-section of a sphere, it's between B and C. Since this conductor has reached static equilibrium, that happens within a nanosecond normally, right? The charge just moves to its location. It finds its equilibrium condition. There's no field on the inside if I'm between, well, let's say, so here, greater than A, less than B, but if I'm greater than B and less than C, I also have zero field as well, because it's in static equilibrium. Well, equilibrium. Electrostatic equilibrium, there can't be any electric field, otherwise free charge would experience a force and move. So since there's no electric field, the flux is zero. Since the flux is zero, there can't be any enclosed charge. And since we know that there's plus Q here, there must be negative Q there on the inside surface. All right. Now, how would we find Yes.
Is there any relation to that being like a negative 2q in the middle being a q, like negative 2 plus negative 1 gets negative 1, or is that just a coincidence?
Negative 2 plus.
Plus the q inside, so like negative 2 plus a positive q gets you a negative q. Is it just like a coincidence that works out that way?
Okay, so how does that work out? Well, how much charge is on R equals C on the outside surface?
Negative 2q.
Well, the whole surface, the whole outside sphere has negative 2q charge. So if negative q is on the inside, how much is left over? Negative q, so how much charge is on the outside surface? Negative q.
Okay.
Yeah, so what you actually have here on this sphere is, you have, on the inside one, it's all, the charge is all like this, right? On the outside surface, you have negative q like this, but you also have negative q like this. That's how the charge would distribute itself. And we kind of use Gauss's law to determine the fact that there is charge on the surfaces like this. Now you might say, well, why is there charge? Shouldn't this conductor right here, shouldn't there be charge? Shouldn't all the charge be on the outside because it's a conductor? Well, this is a conductor with a hole inside of it, and inside that hole there's a charge. And whenever you have that, you can have charge on the inside surface. Yes?
When you say that the electric field is zero, do you mean that there's no net electric field? Or do you, like, because shouldn't isn't there still electric field but of equal, like, in opposite magnitude, so the net electric field is zero?
Yes, exactly. Yeah, the net electric field is zero. Because the electric field, right now, how else would you figure that out? You'd have to use Coulomb's law and do an integral, but using Gauss's law, what we can say is this outside, or this sphere right here, creates an electric field which goes out like this. Right, and in fact, it goes like this, right? It goes through the conductor itself. Now, when I'm inside the conductor, there's a field which points like this, and it cancels out that field, so you get zero field inside. You might say, well, it's negative and negative. How can it create a field that's going inwards? And the reason, just geometrically here, is that there's a tighter curvature here, so the charge density is higher on the inside, which is why the field points towards the greater negative here. Right, that'd be kind of hard to see. I mean, we'd have to do a lot of calculations using Coulomb's law to figure out the field, but using Gauss's law, we have a simple way to determine what the electric field is. So now, let's calculate then the electric field in two other regions, and that would be, R greater than C and R between A and B. And we can do that just by using Gauss's law again. But if I want to find the electric field, let's say in this region right here, I just have to create a Gaussian surface in that region. So I have to go like this. Create a spherical Gaussian surface between R equals A and R equals B. And then I have to apply Gauss's law. And Gauss's law would say the flux through that sphere just equals the enclosed charge over epsilon naught. So calculating the flux, first of all, we have the electric field which can only point in the radial direction because we have spherical symmetry. It can only point directly outwards. Multiplied by the area, which is parallel. Area vector is parallel to the electric field, and this is just going to equal the enclosed charge Q over epsilon naught. Now what we're going to find is, since the electric field is constant over the surface, we can take it outside of the integral because it's constant. And then I'm just integrating over the surface area, and I have E sub r 4 pi r squared equals Q over epsilon naught. So the electric field is exactly what we expect it to be outside. It's Q over 4 pi epsilon naught r squared. So it just looks like it doesn't actually, the shell that's outside doesn't even matter. It's just the only thing that matters is what's inside that shell. Yes?
How come is it that the shell on the outside doesn't draw electric field? Like, how does it not pull the electric field outwards, right, from the center? Shouldn't it, like, the electric field is emanating from the positively charged center, and then it goes to the negatively charged shell between A and B? Between A and B.
Yeah, yeah.
So, doesn't that negatively charged shell pull the electric field as well, in addition to the push from the positively charged center?
Excellent question. So I go back to the question you asked earlier about what's the field in any region. It's the net electric field. So the way to think about this is the key here is the key is the fact that we're dealing with spherical symmetry. Because without spherical symmetry, the argument breaks down. So here's how we think about it is, you're absolutely right that if I was at this point right here, the electric field wants to point outwards, right? But this side of the shell wants to draw it that way. And this side also wants to draw it that way as well. There's only a small solid angle which tends to draw it to the right. In fact, anything that is to the right of that line would tend to draw the electric field. It would make that vector a little bit larger, right? But then we have all this over here, which tends to draw it to the left. And those two contributions cancel each other out exactly. Right? Now, we don't have to know that ahead of time, but that's all, Gauss's law accounts for that. Right? The reason we could make this argument right here and take E out of it, because we know it's constant, has to be, the electric field can't depend on where you are around that sphere, because, I mean, if it was a half shell, for example, then we couldn't use Gauss's law. It has to be that full, complete shell in order to use Gauss's law. All right, then there's one more region to look at, and that's R greater than C. That would be way out here. You know, so way out here, if I want to find the electric field in the region greater than C, I need to create a Gaussian surface which has the same symmetry as the charge distribution again, but it's larger, and it's in the region of where I want to find the field, right? Because I'm calculating the flux through every little patch of that sphere where the electric field and the area vector point in the same direction. So in fact, the calculation is going to be exactly the same as before, exactly the same as this, but now how much charge is enclosed? Negative Q, right? So the electric field then is, it's the same, it's just negative Q over 4 pi epsilon naught r squared. So outside, you know, so once we sketch the electric field, when you're outside that little ball, it just looks like a positive charge. When you're inside any of the shells, it looks 0. And when you're outside the big shell, it looks like it's just a negative charge. Negative Q, and points inwards. Like this. All right. So let's look at an example using cylindrical symmetry. So this is spherical symmetry. Let's look at cylindrical symmetry. And as you might have guessed, Cylindrical symmetry would be charge distributions which look like cylinders. Now, what kind of Gaussian surface would you want to use for a cylindrical charge distribution? Probably a cylinder, right? Yeah. So let's look at an insulating cylinder. And the reason I specify insulating here is because it could have a volume charge density. Right? There could be charge not just on the surface, it could be inside it as well. So insulating cylinder. And I'm going to say it's a really long cylinder. And I'm going to say it has charge density rho. And I'll just make rho constant. So well, actually, let me just make rho. What if it was non-constant? Let me make it just some constant value. I'll call, let's just say it equals A times R. Okay, and the radius of this cylinder is capital R. And it's a very, very long cylinder. So there's two basic regions to find the electric field. We could find E at R less than R and R greater than R. Would be the two regions to find the electric field. Okay, so since this cylinder has cylindrical symmetry, we can rotate it, right? And we can pull it, and we can reflect it about a mirror that's through the central axis, and we don't leave anything unchanged. So our electric field has to have that same symmetry. So let's look at a region that's inside, first of all. And I'm going to create a Gaussian cylinder that is less than R, capital R, I should say. And I'll give it a radius little r. So let's try to find the electric field with little r less than big R. Little r less than big R. I just have to do this right here. So first step, calculate the flux. Now, what direction does the electric field have to point here? Based on cylindrical symmetry, radially outwards, right? And it can't depend on the angle, because you can rotate the cylinder and you leave the charge distribution invariant. It can only depend on how far you are from the center. So our electric field, E sub r, it can only be a function of r. And I'm going to integrate it over the area of the cylinder. And this is going to equal the enclosed charge divided by epsilon naught. Now the enclosed charge is going to be, so I have 1 over epsilon naught. To find the total amount of enclosed charge, let's say that my Gaussian cylinder has length L. So the charge inside it is going to be the charge per unit volume, which is A times R, multiplied by the volume of that cylinder, which is going to be L. And what I'm going to imagine doing here is breaking this cylinder into a bunch of, shells. Or sorry, inside this cylinder, I'm going to imagine breaking it up into a bunch of hollow cylinders and kind of adding them up. So each one of those hollow cylinders has a volume of, well, its length times its width times its height. So its length is just 2 pi r. That's the circumference, and then its width is dr. So I'm integrating this from 0 to r. So I should really make this an r prime. You know, so I'm not using the same variables here. Question?
Is A a constant?
A is just a constant, yeah. Just some constant, and it would have to have units of charge per distance to the 4th power, yes.
What's the difference between R and R prime?
Oh, just limits of integration, you know, because technically you don't want your integrand to have the same as your number here.
Okay, so
This is bookkeeping.
is it A times R prime as well, or is that R?
Oh yeah, it should be r prime. They're all r primes inside there. Yes?
Where did you get the 2 pi r prime from?
So I want to find out, I'm trying to figure out how much enclosed charge is inside the cylinder. So in order to do that, what I want to do is think about how much charge is in a little shell, a hollow shell, and then just add up all those shells. And a little shell is going to have a length of 2 pi r, which is the circumference, a thickness of dr, and then a length of L.
Oh, okay.
So that's where that one comes from there. So this is rho dV, is what this is, specifically for the cylinder. Now again, these could get much more complicated, but it wouldn't get any more complicated than this for us, because we just deal with spheres and cylinders. All right, now that's essentially it. We just have to do 2 integrals, and then we have the electric field inside. So let's just do that. Now here's the trick. This has to come outside again because it's constant. So I have E sub r as a function of r, and then I'm integrating over the area of that Gaussian surface, which is just 2 pi r L. That's the area of that cylinder, and this is going to equal 2 pi a L over epsilon naught, integral from 0 to r of r prime squared dr.
For the area, what about the faces of the circle side of the cylinder?
Oh, excellent question. So what's the flux through the ends of the cylinder?
0.
0. So I don't include those because there's no flux through them.
Right.
Because the electric field has to point radially outwards. But technically a cylinder has 3 sides, 2 ends, and then the curvy side. But the ends have no flux. So then I'm just left with this, and I just have to solve for E sub r as a function of r. Now this integral right here is just r cubed over 3. Okay, now let's just do a little bit of algebra here. So 2 pi cancels with 2 pi, L cancels with L, and 1 r here cancels with 1 r there. So I just have E r as a function of r is equal to, see here, A over epsilon naught r squared over 3. Look correct? Okay, so we found the electric field inside the cylinder for a non-uniformly charged insulating cylinder, right? And it would be very hard. Now, there's a lot of kind of steps that are kind of built in here, and you want to make sure you understand those steps, but look at the algebra here. There's only a couple steps, and we got the answer. Now, to do that using Coulomb's law would have taken several pages. Yes?
Does that say r prime squared dr?
R prime, yeah, r prime squared, dr prime.
And sorry, just for clarification again, r prime is just referencing a different value of r, not the derivative of r.
Well, r,
Or like, try to
I think the confusion here is, do you ever use r prime to mean derivative? Yeah, so I don't mean that here. It's just a different, I just mean a different, well, this, so mathematically, it would technically be incorrect to write an integral like this. Integral from 0 to x of x dx.
Okay, so you're just saying,
Because x is varying, and this x is some limit. So technically we're saying, you know, we can't call them the same thing, so I should call this x naught and that dx naught. Call it something different. But I don't mean a derivative when I put the prime there. Maybe I should just call it a r naught. Question?
so then what does like the r prime represent compared to r?
It's still r. It's still that radial distance.
So in this case, when we're integrating from 0 to r, it would be big R technically?
No, we're still inside the cylinder. So little r is still less than big R, because our Gaussian cylinder is still inside the...
So then what exactly was R prime?
All right, 30 seconds. Explain to your neighbor what r prime is.
Where did you lose the? Oh.
Well, no, we're integrating from like we're integrating like the shell and stuff that's so I think it's the Gaussian.
Oh no.
I think 0 to r is
It's the R from the.
R is
This is R, and this is
that's a Gaussian shell.
It's the shell. It's the shell.
Okay, now the only other region to actually look at is when we're outside the cylinder. And for outside the cylinder, I would make, if I want to know what the electric field is outside, I would just have to create a cylinder which is greater than, I'd have to create a Gaussian cylinder which is bigger than the radius of the cylinder. And everything would go through as similar to before. The only thing that's different is when I find the total amount of enclosed charge, I'm not integrating from 0 to little r, I'm integrating from 0 to capital R. And capital R is just a fixed number. So that means I have an AR cubed L over 3. Now, then when I solve this for the electric field, I have, let's see, A capital R cubed, and then on the bottom I have 6 pi epsilon naught little r. All right, so this is when little r is less than big R. This is where little r is bigger than big R. Now, all right, so I want to get to one more thing, because next class we're going to take the midterm. And then I can take more questions about this at the end of class. But the last thing I just wanted to mention was the idea of planar symmetry. And planar symmetry is important because any surface, if you're really, really close to that surface, it looks like a plane. Or it looks like a flat plane. If you're really, really close, it looks like an infinite flat plane. So planar symmetry is going to be important when you're really near or close to a surface. Okay, so here I have a charged surface.
I see that one thing right
Here I have a charged surface, and I want to find the electric field. So I'll take questions at the end. I need to finish this first. I want to find the electric field right outside of that charged surface, and it has kind of a curvy shape to it. Well, the way I'm going to find the electric field outside that surface is what I'm going to do is I'm going to create a small Gaussian surface so that locally the electric field looks, so locally it looks like an infinite plane. So here's I'll create a little Gaussian surface. Now let's say that this object was in particular, let's say it happened to be a conductor. If it happens to be a conductor, we know the electric field here is equal to 0. So we can use Gauss's law and planar symmetry to find the electric field outside. What we would say is that little box right there, the flux through that box has to all be through the end. Because if you're really close to that curved surface, it looks like an infinite flat plane. It has to point directly away. It has to be normal to the surface itself. So Gauss's law would give us, Gauss's law which says this, for the plane would look like, while the flux on the left-hand side would simply be the electric field, which is pointing perpendicular, multiplied by the area of the end. Now the curvy side, there's no flux to the curvy side here, I don't need to consider it, and there's also no flux through here, because it's a conductor and E is equal to 0 inside, so I just have one side right there. And this has to equal Q enclosed over epsilon naught. Q enclosed is just charge per unit area times the area over epsilon naught. Area cancels. And we find that the perpendicular field is eta over epsilon naught for a conductor. So near the outside. And of course 0 on the inside of the surface. Question?
This is only true if you have a constant surface charge density, though, correct?
No, it's true even if the surface charge density is varying, because let's say there was a sharp corner up here. You would have a larger surface charge density, which would make you do a larger electric field. But it's only true if you're really close to the surface, but outside of the surface. It's going to vary. So the eta that you're putting in here is going to depend on where you are on the surface. It could vary, right? Okay, that's because the surface appears to be flat when you're really close to it and you're only looking at tiny little sections. That's how we can use planar symmetry in this case. So if you have questions, just come and talk to me. But our midterm on Friday, Gauss Law, 26, 27, 28. You can bring a formula sheet and you'll have the full class to work on that. Oh, there's a 2 pi here.
Yeah. So should we both be
Yeah, there's a 3 on the bottom. Exactly. I forgot that 2 pi right there.
Hey, why?
Oh yeah. Thank you. I didn't get it.